So we can put functions together in many ways. We can add them, we can subtract them, and we can do something called composition. So here's the symbol we use for composition of functions. Sounds fancy, but what it means is that G is plugged in to F. Nothing too strange happening here. So let's do an example to illuminate further. And then we'll look at when composite functions are continuous. So, first example, just calculating a composite function. So as I said, you just take G and you plug it into F. That's what this notation means. So in English we'd say F composed with G. Okay, so we just take one function, plug it into the other, so we get F with x plus 2 plugged in. And what's that? Well, instead of f of x, which we have here, we take this x and this x and replace them both with x plus 2. So we got the first x, which is squared, plus the second x, which is not squared. And instead of x, we're putting x plus 2. Okay, and you can work this out. What do you get? You get x squared plus 4x plus 1x is 5x. And then 4 plus 2 is 6. So, composition of functions. Sounds fancy, but it's just plugging one function into the other. So now we want to see, when is a composite function continuous? Well, we have a simple theorem that will guide us here. Here we go. Pause and copy this. So if you have G is continuous at some number, and F is continuous at G evaluated at that number, then the composite function will be continuous. So let's use this theorem to find the continuity of a certain function. Okay, so here we have ln of 1 plus x. So this will be our g, the inside function. So let's look at that guy first. G of x is 1 plus cos x. And where is that continuous? Well, that is just that's a pretty basic trig function, a pretty basic wave function. Now you should memorize what cosine looks like. So cosine would usually look like this, like that, right? But we have this plus 1 here, right? So we're going to take our basic cosine, and we're going to move it up by 1. That's this plus 1 here. So here's a 1, we'll say. And we'll need 2. So 2 is here. And now our new kind of baseline is going like this. And the function goes, should go all the way down. Something like this, roughly speaking. Anyways, the point of this is that I can draw this function without lifting my stylus here, or without lifting my pencil or pen or marker or whatever you're using. So this is a continuous function, and it goes on forever in both directions. So this function is continuous everywhere. So we'll write that down. So g of x is continuous, CTS, everywhere. And in math language, we could say for all. This upside down A means for all. For all. For all x. in the real numbers. Okay, so that's g of x. But what about the outside function? If I have ln of x, this ln of x function is continuous for x bigger than 0. Because, well, I have the graph of ln memorized. It goes through the point 1, 0, and it does this. It does this thing like this. And then the y-axis is what's called a vertical asymptote. So my ln function is approaching the y-axis here, but never touches it. And it doesn't exist at all over here. And it never touches the y-axis. So that's why we have this x bigger than 0. Okay, otherwise over here, the function can be drawn without lifting your pencil. So there you have it. Ln of x is continuous for x bigger than 0. Now I'm going to put these two things together. Let's call them 1 and 2. And we'll see together. Now let's remember our theorem says that my composite function up here is continuous at x equals a if g of a is continuous and f of g of a, and f is continuous at g of a. So putting these two, 1 and 2 together, I see I need well, I basically need 1 plus cos x to be bigger than 0. For the composite function f to be continuous. What does that look like? Well, cos x would be greater than -1. When does that happen? Well, most of the time, actually. If we look at cosine again, here's -1, here's +1. Goes through this point, goes through this point, and then down here goes through this point. So it's going to go It's going to continue waving in both directions forever. And the only time I'm going to hit -1 is at these points here. And there's another one. There's going to be another one over here at -pi. But this function continues forever in both directions. So I'm going to hit this -1 an infinity of times. So let's try to summarize that. So I'll say cos x equals -1 when x equals, well, as I said, it's going to be -pi and also pi. But then over here, you're going to hit it again, right? You're going to hit another one over here at 3 pi. This is pi. It'd be like 3 pi, 5 pi. This was 2 pi here. And if you go backwards, you get -3 pi. And we'll use some ... to indicate that this list extends to infinity in both directions. So cos x equals -1 when x is one of these guys. And looking at the graph here, I can see that otherwise cos x will be bigger than -1. So as long as x is not one of these guys, I'm going to have cos x bigger than -1, and I'm going to have f is continuous. So my answer to this question is x not equal to this list I have here. I can write like that. We have pi, 3 pi, so on. Or equivalently, you could say x is not in this set here. It's another way to write this. Not in. So x is not in this set here. As long as I have that, my composite function is continuous.